Now, so what I'm going to do in this lecture is that I'm going to give you a very brief overview of the Python programming language, especially as it pertains to data science and material science. This will actually form the basis for your first lab in materials data wrangling in Python. Okay. The coverage is essentially a very quick overview for chapters 1 to 4 of the Python Data Science Handbook, which is one of the textbooks that I mentioned. Okay, that handbook, of course, only covers the data science packages, right? So to do data science in material science, you do not just need data science packages, you also need material science packages. And that's something that you cannot find in any textbooks, unfortunately. Okay, the content, at least I have tried to make it as friendly as possible to a beginner in Python. And the idea here is really that you will know enough Python and you have in your mind what are all the scientific Python packages that you will need to basically get started, right? This particular lecture will be extremely heavy on demos and examples. So you can go along with it on your laptop. If you haven't installed Python, the easiest way is to just go to Google Colab and start running. Okay, so that's the easiest. So again, while you can learn coding by just reading and just play around with a few toy problems, it is my experience that coding is actually always best learned when you are actually trying to solve a practical problem. So that would be what the labs are for, right? Okay. So Python is basically a general high-purpose programming language. It is one of the most popular, if not the most popular programming language out there today. The reasons why Python is so popular is very simple, right? It is really the design of the language itself. It emphasizes code readability. So in other words, if you look at a piece of Python code, you naturally can understand what it is doing, much more than, say, if you are reading on a piece of C code or a piece of Java code, right? It supports multiple programming paradigms. So in other words, if you like object-oriented programming, Python supports it. If you prefer functional programming, that's fine too. I myself is more of an object-oriented programmer, okay? It is dynamically typed and the memory is automatically managed for you. What this simply means is that unlike certain other programming languages where you actually have to spend a lot of effort thinking about, well, where am I assigning this pointer, how much memory am I allocating to this particular variable, all these are taken care of for you in Python. You completely do not have to worry about that low-level stuff, okay? It also comes with a fairly large standard library. What this means is that the Python community calls it batteries included, right? So in other words, most of the typical things that you will want a programming language to do, you can do it without having to, say, install an external library, right? Now, obviously, we are not going to just be using your standard library. We actually need some data science packages to help us along. And finally, it is available on almost all platforms. Any OS that you would like to work with, it is almost certainly going to be available on that OS. Okay. Now, to show you essentially how Python, how readable Python is, this is basically an example. So, for example, if you want to do Hello World, which is the first programming problem that everyone does, this is the Java code. There's a lot of, as you can see, there's a lot of overhead. You need to figure out, you need to type this public class hello, public static void. I did Java programming before, so it was a pain, right? And Python, you just basically print hello world, right? Everyone can just read this and you know exactly what this is supposed to do, right? All right, and there are more complicated examples. Now, this slide is somewhat outdated. It was important back in 2 years ago when we were doing this course for the first time, when Python was actually undergoing a transition from Python 2.7 to Python 3. And The reason why this was a problem was because Python 3 actually was backwards incompatible with Python 2. Okay? So nowadays, everything has migrated to Python 3. I don't think it's a big problem anymore. For this course, we will mostly be using Python 3.8 and 3.9 plus. But any Python 3.7 and above, you should work fine. Google Colab is actually problematic in a way because Google Colab actually is, their updates of Python is much slower than the rest of the community. Everyone else has already moved to 3.8 or 3.9. Google Colab is still on 3.7, okay? Now, the good news is we are not doing anything so sophisticated that we need the latest and greatest packages of everything. So Google Colab will still work fine for this course, okay? Now, so as I mentioned, there are two options for this course. If you are intent on doing data science as quickly as possible and you want to be able to do this without internet connections, and you want to be able to have control over what packages, what versions of the packages you are going to install, then definitely you should install Python on your laptop, okay? And the second option is basically you just use Google Colab. This is online Python notebooks. A lot of the packages are already pre-installed for you. You have no installation whatsoever that you need to do. You will, however, be dependent on whatever Google Colab chooses to provide you, and also you will obviously need to be online to use it, okay? Now, if you are going to install Python, the way that I would recommend that you do this is to use what is called the Anaconda distribution, okay? So Anaconda is basically this package version of Python that you can install it like you would install any other apps, okay? There are two versions of Anaconda that they provide. So one is called Miniconda, which is just the minimal version of Python itself plus plus the Conda command line tool. So Conda is basically a package manager, and this is essential for you to install all the packages that you'll be using, okay? There's a much bigger package called Anaconda, and that is essentially Miniconda plus a lot of packages thrown in together. So you can think of this like essentially if you install MATLAB with all the plugins and everything all installed together in one shot, right? It is several gigabytes in size. I never install Anaconda because there's just too much of things that I don't need, okay? So I would actually recommend that you use Miniconda, okay? Now, so I'm going to go through a few basics of Python since most of you have done this before. I will do this quickly. So Python is dynamically typed. So in other words, it is essentially like what you do in MATLAB. You don't declare what kind of variable a variable is. You just simply assign the variable, and Python will automatically try to figure out what the likely variable type is, right? So for example, if you type x equals to 1, that they automatically infers that x is likely to be an integer. If you give it y equals to 2.0, they infer that that's a float. And basically, the other key types that you will need to learn in Python are basically things like strings and a list, which is just a collection of objects. And these objects can be any kind of types. It doesn't have to be a single type. And finally, the most powerful object type in Python, in basic Python, right? And which is called dictionary, right? And a dictionary essentially is a key value pair. In other words, is saying basically A is associated with 1, B is associated with 2, and C is associated with 3, and so on and so forth, okay? Now, there are, other than some basic operations and functions, most of the other functions that you will be using are in packages and modules and must be imported, right? So obviously you can do addition, subtraction, multiplication, and division without importing anything. But let's say you want to do like the sign of a number, then what you will need to do is to import the math package, and the function for calculating the sign is in the math package is math.sine, and then you give it the thing you need to calculate the sine for. So this is of course pi, and this will give you roughly equals to 0. Okay. Now, so this is the Python tutorial. All right. So this is the official Python tutorial. They actually do a pretty good job about introducing you to Python. So I would just skip all the way to number 3. 1 and 2 is really running things on the command line, so I wouldn't bother with that. But if you have no experience in Python, this will actually be a useful resource for you to basically go through what are some of the simple operations you do in Python, and how do you assign variables and that sort of thing. Okay, so I will leave this for you to do in your own time, right? Now, one thing about Python is that whenever you install packages, there are usually dependencies between packages, right? So for example, this version of this package would require another package, but it only works with this particular version, right? And this actually can be quite a complicated process, right? So a best practice is usually to create what are called virtual environments to work in, right? So a virtual environment is just basically an isolated environment containing a set of Python packages, right? And the reason why you would do this is in case you screw up your package somehow, all you need to do is that you basically just delete the entire isolated environment and you recreate a new environment and you start from scratch, okay? Now, both Conda and Python 3 itself actually does come with the ability to create virtual environments. So the way you would do it in Conda is basically you type conda create -- name. This essentially just tells you that you want to create a Python package environment with the name NANO181, and you want to use version 3.9 of Python. Okay, and then you do conda activate. Sorry, this one should say nano2x81. Okay, and that will activate the environment, and then you start installing packages into the environment, and you work in the environment. Now, in case you really corrupt your environment to some in a way that is irrecoverable, what you would do is that you basically just remove the package, and then you recreate the package again, right? And one of the good things about doing conda environments is also that you can actually create reproducible environments as well by using YAML files. In other words, we actually specify exactly what are the versions of the packages you would install into the environment, and you can keep installing the same versions over and over again. And for NANO181, I already have created that YAML file, and you can actually download it in the GitHub repo. Okay, I'm going to come back to the GitHub repo in a short while. Now, we are going to the details of the specific packages you will be using later, but by and large, this is almost a complete list of the packages you will be using for this class, okay? So there is the scientific Python stack, which is basically the packages that underpins everything, okay? So things like numpy, numerical Python, scipy, matplotlib, which is a plotting library, seaborn, which is a statistical plotting library, and Jupyter, which is the notebook library. And the data science packages are essentially Pandas, which stands for Python for data science, okay? Scikit-learn, which is the one that contains all the machine learning models that you will be using. TensorFlow is completely optional, because in this course, all that we are going to do is to go through some very brief introductions into neural networks, but we are not actually going to have lab sessions in the neural networks, okay? So, and you can also do neural networks in scikit-learn as well. So TensorFlow is really an optional installation. And there will be one other package that you need, which is Pymatgen, which is a material science library that I developed, and we will talk about that later, right? And to update the package, all you do is you do conda update that package name, and you basically update the package, okay? Now, as I mentioned, one of the fastest way you can do this is to go to Google Colab, and you can immediately already go through the examples. So I'm going to actually show you some examples, right? Because eventually when you start doing the lab, this is actually quite useful. So almost all the packages that I talked about, other than Pymatgen, is actually come pre-installed with Google Colab. So there is no need for you to do anything else. And if you actually need Pymatgen for a particular piece of analysis that you need to, then you actually need to install Pymatgen in Google Colab itself. Okay? So let me do the examples now. So this is my Google Colab, right? And of course, I can create a new notebook, okay? And this will basically load a completely new notebook. And this essentially is an environment in which you can run Python code in various cells. So for those of you who have done Python but not done notebooks, I think notebooks are actually the nicest invention in terms of usability of Python, right? So for example, you can just run the code and the cells will just run, okay? And this will they will display the outputs of your operations and that sort of thing. Okay, so essentially, this is a way in which you can run Python code, right? And other than just running Python code, the notebook is also a way in which you can add in things like essentially text for you to demonstrate or explain what you're doing, all right? So that is why for our course, I'm actually going to use Jupyter notebooks a lot, right? Now, so this is if you are starting the notebook just from scratch, you can do that, okay? But you can also, you can also open a notebook, right? So the way that we can do this is, as I mentioned, for this course, we already have a GitHub page for the course, right? So my group is called the Materials Virtual Lab. So all my group's public repositories are under that organization, which is the Materials Virtual Lab. So all you need to do is to type the Materials Virtual Lab organization. You will see a list of repositories that you can actually access. The one that you will be interested in is this one called NANO181. Unfortunately, GitHub doesn't allow me to easily change the name of a repository. So I'm going to keep the NANO281, but both the NANO181 and NANO281 people are going to be using this repository, right? All right, so now once you actually go in there, you will be able, it will list out all the notebooks that are in this repository, right? So, and you will see that I've actually already prepared the notebooks for all the lectures that you'll be doing. So let me, so all the way to lecture number 9, right? But let's start with the first one. If you just click this one, what this will do is basically it will now open up a copy of that notebook on your own Google Colab, right? Now, you do not need to worry. You can always change any cell you want just to play around with it. You will not affect the GitHub repository. Basically, none of you will have writing edit rights on the repository. So there's no way for you to change the repository stuff, right? Now, this is actually a very good way for you to quickly get into the relevant notebook for a lecture. So let's say when we get to lecture 3 and we are learning about linear methods, you can also open up the lecture 3 linear methods notebook, and then you can follow along the examples, okay? Now, this is what I mean by a notebook being extremely useful. So for example, I can create cells like this, where essentially using a language called Markdown, I can, for example, type a text to say, well, this is my basic introduction into Python types, okay? And you can change the type of the box, okay, by selecting whether this is a code or a text, okay. So in this case, this is obviously a code box, a text box. So in other words, for your lab, for example, what you might do, for example, is that you will write some code to solve one of the lab problems, and then you will need to explain what you have done, right? You will need to tell me, well, based on this analysis, I think that this result is telling me this. So you can use your text boxes to basically explain those things, okay? Now, as I mentioned, we can run code in the text, okay? So, well, they say this notebook is not authored by Google, but it is authored by me, so you can trust me, right? So you can just run the calculations, and you can essentially run the squares. You can run operations like z times y. Now, you do need to learn some. For those of you who are not familiar with Python, you need to understand that, for example, Python uses zero-based indexing. It doesn't use one-based indexing. So those of you coming from MATLAB uses one-based indexing, right? So Python uses zero-based indexing. So for example, this says that I want the item number 3 in the list. This is 0, 1, 2, 3, so it should actually be A, okay? So this actually prints out the third item in the list. The index of number 2 is actually 1, okay? And you can also just concatenate this by adding them together, okay? So this notebook essentially just demonstrates to you some of the basics of Python. So like for example, dictionaries are essentially just key value pairs, okay? So this basically says I want the item in the dictionary that's associated with the key C, okay? So obviously if you look at here, it should be 3. And indeed, if you run this cell, it actually gives you 3, okay? Now, for those of you who are not familiar with Python, one of the things that you will notice is that there's these green areas. So anything after a hash is basically a comment, right? So it has no effect whatsoever, right? And so this is usually a very good way for me to comment the code such that you understand what the code is doing, right? All right. Any questions so far regarding Google Colab or Python? If not, all right, I'm going to move on. We will not talk about Pymatgen for now until I get that done. All right. So the first thing I'm going to do is I will leave all of you, especially those of you who have no experience in Python, to go through the Python tutorials. But I'm now going to give you a very quick overview of all the scientific Python and data science Python packages, right? So these are essentially the entire list of things that you will be using in this course, okay? Jupyter is basically a software for interactive computing. Basically, it is the back end for that notebook that you just saw. If you are using Colab, that essentially is what you see in Google Colab. So there's no need for you to worry about it. But if you are running Python on your notebook, on your laptop, then you will actually run Jupyter to run the notebooks, okay? NumPy and scipy are essentially the fundamental packages that almost all scientific Python is based on, okay? So NumPy basically is just a Python, a package that defines things like matrices and arrays, and how do you perform basic operations on them, like dot product, matrix products, eigenvalue decompositions, and that sort of thing. Scipy is a much bigger package. It's much more complex. It does things like efficient numerical routines for things like optimizations, integration, differentiation, and that sort of thing, okay? Now, anyone who is working on Python, on data science in Python, will be familiar with the Pandas package. So it seems that only a very small fraction of you have ever touched Pandas. So Pandas is you can think of it as essentially a Python version of an Excel table. It is much more powerful than an Excel table, but it is something like a Python version of an Excel table, where you essentially have your data in columns and rows, and it makes it very easy for you to do manipulations of that data. Okay? All right. Scikit-learn is basically where you actually have all your machine learning packages. So things like your linear regression models, your kernel models, your tree-based models, ensemble models, and even neural networks. Okay, you will be very familiar with this by the end of lecture 3 or 4. Right? Okay. TensorFlow is completely optional. This is basically a Google package for developing ML models. If you ever are interested in developing your own machine learning models and you want a way to do it in an efficient way, TensorFlow would be one option. The other option is things like PyTorch. Okay. And finally, the last two packages would be, again, something that you will use very often in this course, which is matplotlib and seaborn. Matplotlib is the de facto plotting library in Python. You use it to essentially plot things like scatter plots and whatever, line plots, bar plots, whatever you want, right? Seaborn is just a package that makes all that a lot easier, right? So I'm going to demonstrate it. Essentially, it is a way for you to just say, I want to plot the relationship between x and y in a scatter plot, and seaborn will just allow you to do that in one line rather than having to do like 10 lines of matplotlib code. Okay, so this is actually a very powerful package that I really like. Okay, I'm going to give you a very brief background on all the packages. I'm going to focus actively on actual demos. So it is not possible in this course, of course, to comprehensively cover all the functionality of every single package. A lot of them are so big that it will take you, even now, even today, I still don't understand every single functionality of every single package, okay? So you will basically be, I'm going to just give you a brief overview of the functionality that you will be using, okay? My focus will be on what are the general modules and methods that you may be using, but I want to make it clear that an expectation of this course is that you yourself will be reading the documentation to figure out what methods to use. Okay? So I want to make that clear because sometimes people think, oh, well, you're just going to tell me use this particular method call to do this, right? Sometimes it's not so simple. You actually have to go into the documentation, figure out, well, this method call requires me to call it with this particular set of arguments and keyword arguments, and how do I specify that, okay? So again, Google is your best friend here, so please do that. You will be, NumPy and scipy are basically the backbone of a lot of the other packages like Pandas and scikit-learn. You just need to roughly know the basics of NumPy arrays and how to perform some simple operations. In most instances, you are actually not going to be using the lower level NumPy operations themselves, okay? In most cases, the package that you will be interacting with most often is scikit-learn. All right. So Jupyter notebooks, right? So as I mentioned, if you are using Google Colab for this course, you don't actually need to run Jupyter notebooks. If you do install your own virtual environment with Jupyter, then Jupyter notebook essentially is what I just showed you. All the lecture examples were made in Jupyter notebooks, and you will be using them to do your labs and submit. You are submitting your Jupyter notebooks as the lab report, okay? So let me first demo what happens if you run a Jupyter notebook, right? So to run a Jupyter notebook, what you will do is that you will type Jupyter notebook, right? And basically, this will just call this, and you can create a new Jupyter new notebook itself, okay? And essentially you can do what I just showed you just now, and so on and so forth, and you can run the code, right? So essentially completely no different from what you see in Google Colab, right? Okay. The difference is, of course, this is running on your local machine, and you can do it even when you're not online, okay? And that's all I have to say about Jupyter Notebooks. Oh, I do want to talk a little bit. I think it will be in the next slide. Okay, now, if you have not used Jupyter Notebooks before, since I think only half of you, even those with Python experience, have used Jupyter Notebooks, you do need to understand there are certain special features of the Jupyter Notebooks that make them extremely useful, okay, especially for newcomers to Python. Now, to run the code in a cell, you just press Shift and press return, okay, so that's easy. Now, one of the most useful things about a Jupyter Notebook is what is called tab completion. In other words, you just need to type the first few letters of something, and you press tab. It will actually show you what are the options. Okay, I'm going to show you later. There are also magic functions. Magic functions are essentially just code that can call up things like help documentation or execute certain functions or that sort of thing, right? Now, for you guys, the most important one that you want is question mark, okay? Because question mark just brings out the documentation, and you can immediately know what that method is supposed to do without having to Google, okay? As I mentioned, you can write text and narrative, and you can also make plots in the notebook itself, and you will just display in the notebook. Okay, so it is very useful for code prototyping and data analysis. Okay, so let me now go back to my Google Colab. Okay, I just want to show you what is meant by the question mark. Okay, so actually, I'm going to zoom in because otherwise I'm afraid that you guys cannot see this. Okay. Now, as I mentioned, there are some magic functions that you guys should be aware of, one of which is the question mark, right? So let's say I import math, and I do not know what math is supposed to do. So I can just type this. Oops. Why is the code completion not working here? So let me first show you the magic function, which is question mark, right? So let's say I want to know what the sign function does, right? And I want to call out the documentation of the sign function. All I need to do is I type math.sign, and I put a question mark, and you will see that basically it comes up with this thing, which tells you return the sign of x measured in radians. So this tells you actually useful information, right? You know that x has to be in radians and not degrees. It tells you the method signature. Basically, you just give it x. And it tells you what the return type, right? And so, of course, this is a very trivial example. Everyone of us know what the sign function is. But once you actually get to running things like numpy code and scipy code and your scikit-learn code, this function actually becomes very, very useful, because then you can call up and understand what exactly is the method signature and what that particular method is supposed to do, okay? All right. I'm actually confused about something. Why is there no code completion? Okay, let me... All right. It seems that Google Colab has some limitations, but let me show you what code completion, tab completion means. So for example, if I'm running a Jupyter Notebook on my own local machine, and I want to know what are some of the methods available in the math module, I just type math dot and I press tab, you can see that there's now a drop-down list, which gives me basically a list of all the functions that are available. Okay. Again, this is very useful for quickly writing code, right? So sometimes I'm lazy, and I'm done. Okay, rather than having to type out the whole function names, and some of the function names can be really long. Okay, so this type completion feature is actually extremely useful when you are writing your code. I will try to figure out the type completion for Google Colab later. I'm sure they have it. Otherwise, it's a severe limitation. Okay. All right. Now, so the first package that I'm going to go through is NumPy. And as I mentioned, this is a package that you need to understand and you need to know the basic operations. It is underlying basically all the other packages that you will be using. It is, however, not something that you will interact with too much, right? So basically, NumPy implements the array and matrix objects. The underlying implementation is actually in C, so it is extremely efficient. Despite what people will tell you, that a lot of people complain that Python is slow, it's only slow if you are doing it in pure Python. So if you have underlying implementations in C and you just have a Python API, those code are as fast as what you will get in C. Okay. One of the key things about using NumPy is that vectorization of operations is actually key to efficiency, right? So refrain from using for loops, okay? So whenever you have the temptation to use a for loop, think about it whether you need to use the for loop. You use the for loop, things will be slow. If you use a NumPy vectorized operation, it will be fast, okay? I'm going to demonstrate that later. There are two types of objects in NumPy. One is called array and one is called matrix. Matrix is what you guys will be familiar with from your linear algebra. It's basically the matrix in linear algebra. The problem is that actually in Python is extremely unhelpful to think of things in terms of matrices. Okay, so do not use the matrix object. Ignore the matrix object altogether, and just focus on the array object. All right. Now, the cost of just focusing on the array object, though, is that to do things like dot products and vector products and that sort of thing, you actually need to call special methods to do those dot products and vector products. Okay, so unlike matrices where you can just do times and they know that it is a matrix multiplication, you do need to do special operations for that, right? Now, for Python 3.7 and above, you can there is actually a new operator called add, and that actually is a matrix multiplication operator. All right. Now, for those of you who are not familiar with Python but are extremely familiar with MATLAB, I actually like this. It's called NumPy for MATLAB users. Okay. So if you actually go to this webpage, you find that they actually give you a line-by-line comparison of MATLAB operators and Python operators, and it is very useful for you if you are completely new coming into Python, just so that you understand what are the equivalent commands for both MATLAB and Python. Okay. All right. Now, this is a very basic example of how you do things in NumPy. So the convention is that you will import NumPy as NP. Okay. What this simply means is that wherever you see NP inside the code, that just means that I'm using the NumPy module. Okay. So to create an array, I basically say x equals to np.array. I give it an array of numbers. And array here is basically a matrix, which is a two-dimensional array. It is a 3x3, a list of three lists. Okay, so it's a nested list, right? So each list item has 3 items, and we have 3 of this list, and this basically gives me a matrix. Okay, and so I define one array and I define another array, and what you will notice is that if let's say I do a simple multiplication operation on x, what I get is not a matrix multiplication. So I have to stress this, right? This is not a matrix multiplication. It is actually an item by item multiplication. So x times x just means that I'm going to take this and I multiply it by itself. So basically, it's 1 times 1 gives me 1, 2 times 2 gives me 4, 3 times 3 gives me 9, and this is essentially what you get here. Okay, so this is not a matrix multiplication. To do a matrix multiplication, you need to use a function called the dot product, right? So, and this actually gives you the dot product of that matrix with itself. Okay, so this is the cost of using arrays rather than matrices, but arrays are actually a lot more flexible compared to matrices. Okay. Now, obviously, no linear algebra package is going to be complete if you cannot do things like getting inverses and that sort of thing. So, to get the inverse of a matrix, you just use the linear algebra module in NumPy, and you type inverse, and you get the inverse of the matrix. Okay. So, I'm going to just go through the NumPy examples, and then I think we can call it a day for today. So let me go back to my Google Colab, right? And I'm going to close this help. And this was the code that I just showed you. Oops. The reason why this happened was because I didn't run this cell. And so this is how you essentially define an array. And this just shows you that the operations are all element-wise. Okay, so in other words, you do element-by-element operations. Addition, multiplication, all are element-wise. Okay, this is your dot product. Okay, and you can also do the dot of a matrix with an array, which is essentially just your vector multiplication. Okay, and that gives you this is basically the dot product of your matrix X with your vector Y. Okay. Now, in Python 3.7 onwards, there's this add operator. That's basically your matrix multiplication. So if you are lazy, you can do this as well. So this is the matrix multiplication of X with itself. This is the matrix multiplication of X with Y, and the answers are the same. Okay. So, and you can get your inverses. This basically shows you how you get your inverse of a matrix with NumPy, and you can calculate things like the eigenvalues using the EIG function. Okay, so again, this is actually a good case where it's useful for me to show you what the question mark does, right? So if let's say I want to know what this method has, so you see that it tells you the method signature is just basically NumPy linear algebra eigenvector of A. It gives you the eigenvalues and the right eigenvectors of a square array, and it tells you what kind of things, parameters you need. Okay. Oops. And what it returns, right? And you need to note that what it returns is actually something not so simple. It actually returns not just the eigenvectors, but also the eigenvalues as well. Okay? So in this case, what you see here is that what has been returned is both the eigenvector, eigenvalues, this is basically a series of eigenvalues, as well as the eigenvectors associated with those eigenvalues. Okay? So again, this is a good way of demonstrating the power of this question mark power function. Okay. Now, as I mentioned, NumPy vectorization is the key to efficiently coding, right? And this is actually critical when you are actually doing your machine learning models. If you try to do a lot of for loops, your training will be very, very slow, right? And I can show you this very easily using an example. Okay. So here, what I'm doing is that I'm just generating a random series of 10,000 numbers, okay? And let's say I want to compute the mean square of those 10,000 numbers, right? And obviously, you know, this is something that you would do, right? Every time we want to minimize something and we want to calculate the mean square error, you need to first calculate the mean square error, right? And 10,000 data points is by no means large. This is actually a very common thing that we do, right? Now, Jupyter notebooks come with this function called time. So if you do percentage time, it will basically tell you how long it took to execute that particular line of code, okay? So I show you 3 ways in which you can do this. You can do this using a for loop, which is step number 1. you can do this using numpy functions, which you just basically do element-wise power of 2 of everything in the array. Then you sum them and then you square root them. Or there's also a numpy function called norm, okay, which also calculates the same thing. And you can see that, well, if I do the for loop, which is the dumb way of doing this, it took 25 milliseconds. When I actually do this vectorized way, I get about 1.27 milliseconds, so already a factor of 25 times faster. And this is 89 microseconds, but that's mainly because it's done in the backend in C code. Okay, but this basically just shows you that vectorization is actually very important. Do not use for loops unless you have to, right? So scipy is essentially the sister package to numpy. It stands for Scientific Python. It defines beyond what the capability that numpy actually provides. Scipy also provides numerical routines for things like integration, interpolation, optimization, linear algebra, statistics, so on and so forth, right? So, for example, one of the ways that you might use scipy is to generate statistics such as a Gaussian distribution or a uniform distribution, and you then use those numbers to do your machine learning, okay? There is actually a linear algebra package in scipy that is just a superset of the functions in numpy.linear algebra. The benefit of using scipy is that it is always compiled with the LAPACK and BLAST libraries. That means that potentially it can be faster than the corresponding numpy routines, right? Now, for your purposes, you are not going to be doing anything super heavy duty, so don't worry about that small performance gain you are going to get from scipy linear algebra, and you can just use your numpy packages, okay? Eventually, if you happen to one day go work for Amazon, Google, Microsoft, and you are writing big machine learning algorithms that work with millions of data points, then yes, you might want to worry about performance limitations, okay? Now, it is actually a dependency for most. Scipy is actually a dependency for most of the packages you will be using. So here I'm showing you an example. The scipy package has a stats package. And using the stats package, you can, for example, generate something like a Gaussian distribution. This basically says stats.norm 01 just basically says that I'm going to generate a normal or Gaussian distribution with a mean of 0 and a standard deviation of 1, right? And using that distribution, you can then calculate things like the cumulative distribution function values and so on and so forth, right? So you can imagine that this is actually highly useful, right? And if you have taken a statistics course before, you know that you always refer to the CDF values for estimating your hypothesis, doing your hypothesis testing and that sort of thing, okay? Scipy also has a constants package, and again, this is the other package that I find myself constantly using, pun intended, for material scientists, right? Because one of the things that we always want to get is things like the physical constants. What's the value of the electron charge in coulombs? What's the value of Boltzmann constant? What's the value of the gas constant? Speed of light, okay, for example, right? And this constants package actually have all these, have more than 100 physical constants all built into it, right? And these values are constantly updated, so if CERN measure a new value of the gravitational constant, here is basically where you will see it, okay? And so this is something that is extremely useful, okay? Now the documentation for, I did give the documentation for scipy in the link, so you can just click on it in your slides and you should be able to go through it. And there is actually this very useful resource called the scipy lectures, and if you go to their website, you will basically, there's this entire series of lectures talking about Python for science, how you actually go about using numpy, doing plotting in matplotlib, using scipy for high-level scientific computing, and if you intend to actually go deep into all these packages, this is actually a highly useful resource. Okay. All right. Now I'm getting to the package that you will be using a lot in this current course. Okay. So numpy and scipy, like I said, they work behind the scenes. You may or may not use them directly. You may just use small parts of them, but you will definitely be working with pandas. Okay. Now, pandas is basically a library that is used for data analysis. What pandas does is that it defines data structures that are designed for working with relational or labeled data. What that simply means is that you can think of the pandas data frame as something like a Python version of the Excel table. Okay, and there are two main data types. One is called the series, which is just essentially a 1D array. And there's the data frame, which is a two-dimensional labeled structure. And it essentially is like an Excel table or Excel sheet. Okay. Now, like I said, the data frame is essentially what you think of as an Excel spreadsheet. There is also a data frame object in R. So that's the other big data science package that a lot of people uses. I prefer Python because for a lot of the scientific stuff, like things like doing material science, you don't actually have libraries in R, or rather I don't know of any libraries in R to do material science analysis. Okay. Now, if you want to get a quick guide to pandas, there's this thing called the 10-minute guide to pandas. It is very useful. If you go through it, let me just click on it and show you what it actually is. Oops. Oh. So seems like pandas themselves have removed that particular thing. But I'm sure if you search on it, you can see things like this thing called Getting Started. Okay. And they will talk about how to use it. I will actually show you some examples later. Okay. So there is actually a documentation in the they actually have tutorials. So now it's actually a lot more sophisticated, right? So what kind of data does pandas handle? It actually tells you how do you think about a pandas data frame object, and how do you construct the data frames given a set of data. You usually would not construct a data set this way. This is by far the most inefficient method to construct a pandas data frame. I would say nearly 100% of the time, you will basically construct a pandas data frame by reading in from an Excel file or a comma separator value or from the web. Okay, so this is just for small data sets where you just want to play around with a few small things. Okay, and essentially they will show you what's the difference between a data frame and a series, and how do you do some things with a data frame, and so on and so forth. Okay. I'm going to go through some examples in my own way later, right? Now, so I'm going to do a pandas demo because, like I said, it is such an important part of your this course that you should definitely know how to use pandas well, right? So for this demonstration, I'm going to utilize data that has been published by the Material Simulation Toolkit on this resource called Figshare. Now, for those of you who do not know what Figshare is, contrary to the name, Figshare is not a place just to share figures. Okay, Figshare is essentially this open site where nowadays, if you are a scientist and you are publishing a paper, and you need to send your data somewhere rather than attaching it to the publication, right? So for example, let's say you have lots and lots of data on COVID vaccination statistics, right? You would actually put it on Figshare, okay? So, or at least Figshare would be one of the places in which you can put it, right? Now, the Material Simulation Toolkit is done by this group out of University of Wisconsin-Madison. So they have done calculations on a lot of perovskites, and So here what we are going to do is that we are going to download this data from this particular website, okay? If you look at this, this is the website that I'm going to download the data from, right? If I go here, and you can see that now the file has been downloaded, and this is basically a data file of solid diffusion barriers in various materials. Okay, so you can see that this is actually a huge Excel spreadsheet. Okay, it essentially gives you data on if you have, for example, a silver matrix and you have cobalt diffusing in the silver matrix, what would be the diffusion barriers, and then they also give you some various data points about the sites themselves. So things like the electronegativity of the different elements, what's the Mendeleev number, number of valence electrons, and so on and so forth. Okay. Now, so the actual nature of the data is not important. Okay, so right now we don't focus too much about the material science content of the data. What I'm trying to show you is how you would actually go about using Pandas to read in the data from that file, right? So we are going to use a package called request, which makes it easy to get the file. So you use request.get, that you give it the URL, and you get the raw text, and you can then use Pandas to the method called read CSV, which is read comma separated values, and you give it the raw text, and what you would then get is basically the Pandas data frame. Okay. Now I'm going to show you this directly in the code itself. Okay. So let me go to my Safari. So this is Google Colab. So we have already gone through the numpy and scipy packages. So I am going to skip past those. So this is the exact Pandas code that I just demonstrated. Okay. So what this code is doing is that it's basically getting the data from this file. It uses request to get the raw data, which is the text, and then we use the pandas.readCSV method to basically parse the file and then read it into a Pandas data frame. Now, you can display the Pandas data frame in a Jupyter notebook using the display command, and this is basically what you get. Okay, so this is your Pandas data frame, and you see that you have all your the exact data that you actually get from that comma separated value file. Okay, now you also see some statistics. We have 408 rows, okay, and 29 columns of data, right? Now, so this is just one of the users, and after that, you can actually get each of the columns. Let's say I am just interested in this particular column called enorm, all right? And if I want to get the enorm, all that I do is that I do the data frame, which is data. I use a square bracket, and I give it the name of the column. So this is enorm brackets EV. So the name of the column is actually the whole text over here, and you basically get that whole column, okay? So, and this column is essentially what Pandas call a series object. Okay, so it is a one-dimensional array of data, right? And very frequently you will want to plot one series against another, or you would actually want to use one of the series as the target variable for your machine learning model, while you use the other parts of the table for your features. Okay. Now, you can also do very, very useful things. Like, for example, let's say you will see that I actually have data that are positive and negative, right? Let's say hypothetically you only want structures where the E norm is greater than 0, right? So you can actually do a filtering very easily like this. You can say, well, I'm going to get from the data data frame, I'm going to select all the data that satisfy this condition, which is that the column itself, the enorm column, is greater or equals to 0. Okay? So what this does is that it then basically filters out only the relevant columns, and you would then set it to this variable over here, which I just name it df. Okay, you can name it whatever you want, and then here I show you another very useful Pandas operation, which is called describe, right? And what the describe method does is basically it describes the statistics of each of the columns. Okay, so here you see that it describes what's the number of data points. So 177. What it simply means is that we started off with 408 rows. After we have filtered out all the data where the E norm is greater or equals to 0, or rather we filter out retaining only those that the E norm is greater or equals to 0, we only have 177 data points left. Now, then there is also the other statistics that you might be interested in, so things like the mean, the standard deviation, the minimum, the maximum, the quartiles, right? So you can see that this is the 25 percentile, 50 percentile, 75th percentile, the maximum value, and so on and so forth. Okay? All right. Yeah?
Why do we have to call data twice? Why can't we just put, just add greater than or equal to 0 at the beginning for the top?
Great question. Okay, so the bracket basically filters out what the variables you want are. Okay, so let me show you what happens when you don't actually filter that out. Okay. Okay, I'm going to move this down. And let me show you what happens if you just do this, right? So this is what is inside that square bracket. If you do this, oops, oh, did I not run it? Oh, maybe I didn't run it, but that's a small thing. Okay. All right. So what this does is that it generates a column which says whether 0 is true or false, and whether this particular row is true or false, which means is this row greater or equals to 0? Which means if it is greater than 0, this will be true. If it is not greater or equals to 0, it is false. And then you then use this to filter that particular data, which means then what will happen is that the data frame will only retain the rows in which that value is true. Okay, so an alternative way of doing this is that if this makes it clearer, I can say I set this to be equals to the condition, and I am only retaining the rows in which the condition is true. Okay, so this is the way to think about why there's two data index.
So the first one is just a Boolean array?
It's just a Boolean array, and the Boolean array then is used to filter that data frame. Okay? All right. Any other questions? Yes?
If there is for the energies, if there is a specific 10 numbers I really want, can I filter this 10 numbers out?
Yes, you can. So let me show you how to do this. Okay. Instead of filtering 10 numbers, let's say I only want the data in which the material composition one is silver. Okay. So I can do that. I can just say that the condition would be material composition is equals to silver. Okay. And what you see here is that there is only 11 data points for which that is true. Okay? So, and yeah, there are various ways in which you can do this filtering. But you can also select subsets of values. You can imagine that if you do this multiple times, you essentially can get the different sets of values. Okay? All right, any other questions? All right, if not, let me, now I have to reverse what I just did. Okay. Okay. So one of the things that Pandas comes with is also some very useful, quick ways of plotting data, right? Obviously, the results are not going to be as good as you customizing your plots in matplotlib or seaborn. But if you just want to get a quick look at the data to figure out whether there's any relationship between certain columns and that sort of thing, you can just call, let's say, take the data frame. I would like to plot. My x-axis will be my enorm EV, and my y-axis will be my e-raw EV. And the kind of plot that I want to use is a scatter plot. And basically what you get is something like this. Okay? So just a very useful method to quickly get a plot of the data. There is also ways in which you can plot bar plots, you can plot line plots, and so on and so forth. You can see that this plot generally is very ugly. So if you are writing a paper for a publication, this is not a plot that you will want to submit to the journal. But it is useful for yourself when you are actually going to just doing data analysis and you just want a quick sense of the data. Okay? All right. Any questions? If not, I'm going to come to the second set of packages in which you will be using, I would say, even more than Pandas in this course, and that is called scikit-learn. Okay, so scikit-learn is basically a package for machine learning. So it defines things like the machine learning models, like what is a linear regression model, what is a kernel model, what is a decision tree, what is an ensemble model, random forest model, what is a neural network, or more formally called a multi-layer perceptron. And you essentially use scikit-learn to do a lot of the, to train a lot of the machine learning models that you will be doing over in your lab, okay? Now, TensorFlow is a more specific package. It's actually a bit lower level. It is developed by Google, and their specialty is, of course, building deep learning models, things like neural networks, convolutional neural networks, and so on and so forth. And TensorFlow is a package specifically for that purpose. Okay. Now, for the purposes of this course, you are not going to be touching TensorFlow much at all. I will show you some examples just so that you are aware. You will mainly be using scikit-learn for machine learning. Now, there's a very good reason for that, which is that the scikit-learn API is actually a lot easier for everyone to learn, and because it's very standardized. Okay, every single model is basically I create a model, I call the method called fit, and then I call the method called predict, and that's it, right? So it is very standardized, and all you need to worry about is things like how do you do cross-validation, how do you do your hyperparameter optimization, and so on and so forth. Okay. Now, I'm not going to show you any examples on scikit-learn right now because in 2 lectures from now, when I actually start talking about linear models, I'm going to go through detailed examples of scikit-learn. Okay. So so here I'm just making you aware that this will be the package that we are going to work with in this course. Now, I just want to briefly touch on the scikit-learn model API, and I'm going to come back to this when we go on to the linear models. So almost every single model that you're going to be using in scikit-learn, they follow the same basic principles. Okay? You will basically initialize the model by calling the name of the model with some parameters. You can get the parameters using this getParams method. You can set the parameters using the setParams method. You will fit the model using a fit method. So x and y will be, this will be your features and this will be your target. And then you can score, which in other words, you can calculate things like what is the accuracy of your model. If you're doing a classification, you can calculate things like the root mean square error, or you can do things like the mean absolute error using this score function. You can then also make a prediction given some set of data using the predict method. Okay, and no matter which model you are going to learn in this course, it doesn't really matter. Linear regression, decision trees, ensemble models, they are all the same. Okay, these method names are all going to be the same for every single model, right? So that's why I use scikit-learn for the purposes of teaching this course, because it is very easy for beginners to get into. you know exactly what method you need to call to do everything, okay? The only thing you need to worry about is basically the parameters that you can set for different models are obviously different for different types of models, okay? So things like decision trees will have a different set of parameters compared to a linear regression model compared to a neural network, okay? All right. Now, the final set of packages in the scientific Python list that I'm going to talk about is basically your plotting packages. So this is actually a critical part of this course because ultimately, the best way in which you know how well your model is working beyond just looking at just a number like mean absolute error is really just to plot out the data to get a sense of how good the predictions are, right? So there are two plotting libraries. Matplotlib is the de facto library that everyone uses, and even other libraries like seaborn actually uses matplotlib as an underlying package, okay? So you can generate anything you want using matplotlib. The problem with matplotlib is that the API is very low level. What we mean by that is that sometimes it takes a lot of customization to do what you want it to do, right? So for example, let's say you want to plot, do a plot with two different axes with some shading here and a different Gaussian fit distribution fit over here. Doing it in matplotlib may take you like 100 lines of code, okay? Now, seaborn, on the other hand, is the opposite. It is a package that is very specific. It is meant for statistical data analysis, okay, visualization. And it actually works very well with a Pandas data frame. So you can, for example, plot a distribution plot using things like seaborn.displot, and you give it the x. You can do scatter plots like if you give it a data frame called materials, and you tell it to plot the melting point versus the modulus, you can just plot it like that, okay? Now, one of the nice things about seaborn is that it actually comes with a gallery that shows you what kind of plots are possible, right? So all these are the different kinds of plot that you can do in seaborn, and they also have very helpful code examples. So let's say you look at this and you say, wow, this looks nice. I want to use that for my research paper. So I will click on this, and they actually will have an example code showing exactly how that plot is done, okay? So this is a useful resource. When you are actually working on plotting your lab data, please look at this and choose the most appropriate plotting types of plot that you would want to use, that will show your data in the best way, okay? All right, let me go back to the Colab. So here I'm just showing you one example in seaborn. So this just takes the data frame that we actually have just now, and let's say I want to know what the distribution of the enorm series is. So I asked it to do a displot, which is a distribution plot of the enorm series, and this is basically what comes out with just a single line of code, right? Now, to do this, again, to do this in matplotlib is not impossible. It's going to essentially take you, I would say, at least 10 lines or more, okay? But here with seaborn, you can just do it in one shot, right? Now, you see that the distribution is such that every value is greater than 0. Obviously, that's the case because I already filtered out the values that are smaller than 0. So this is just the plot of the values that are greater than 0, okay? You can do the scatter plot as well, and you can see that this is basically a scatter plot, and this is essentially similar to what we have right here, okay? This is just a different way of doing the plot, okay? All right. Now, finally, I'm going to come to the last package that we need to cover, which is your packages for materials analysis, okay? So now, if this is just a pure data science course, general data science course that just teaches you how to write machine learning models to work with arbitrary data, like things like data from Facebook pages or Twitter, then you probably will need this, right? But because this is specifically a data science course for material science, you do need libraries which will actually help you do some of the material science analysis, all right? Now, the package that we are going to work mostly with in this course is called Python Materials Genomics, or Pymatgen. Now, this is actually a package that I myself started when I was still a grad student back in 2010. And it has grown into basically one of the most widely used material science libraries out there. So the downloads are in the hundreds of thousands, okay? And this is the core materials analysis library that powers the materials project today, right? If you do not know what the materials project is, I'm going to talk about the materials project in our very next lecture, okay? But basically what Pymatgen does is that it defines things like Python objects for materials data representations. So things like what is an element, what is a composition, what is a structure, how do you calculate the distances between atoms, so on and so forth, okay? It also provides methods to do structure and thermodynamic analysis, things like calculating phase diagrams, and various other kinds of analysis that you will want to do. It is completely open source, so anyone can download and use it, and people also collaboratively develop on it. What this means is that I frequently, as the maintainer of Pymatgen, gets a contribution from a complete stranger saying, well, I have this new interesting analysis, maybe someone else in the material science community might want to use it. Do you want to integrate it into Pymatgen? Okay, and I actually do that, right? And the part that you will be using a lot in this course is this last part, which is it actually provides you with high-level methods to access what is called the Materials Project API, or Application Programming Interface. Now, what the Materials Project API is that it is essentially a way for you to programmatically get data from the materials project, right? And you can download very large quantities of data from the materials project using the API. And with that, you can then do all sorts of interesting machine learning and data analysis, okay? All right, this is just a very quick overview of the capabilities. Typically, the way that Pymatgen workflow works is that you will start reading in your structure or data from some input sources. So things like, if you are like me, a computational material scientist, you read in your calculations from the input or output files from your calculations. You can also read it from various formats that are commonly in use out there, so things like the crystallographic information format or the Open Babel molecule formats. And basically you can then get Python objects out of them, so things like representations of structures or molecules, computed entries, which is basically a container for calculated data, things like representations of the DOS or band structure. And then you can do, and one of the other major sources is of course the API from the materials project, and you can then do all sorts of analysis on them after you convert them into Python objects, okay? All right, now I need to demonstrate to you how to use the materials project API. This is a very brief demonstration. It is not in detail yet. You will need to do this later. So the materials project API is accessed using the pymatgen.ext.matplotlib.empty raster class. Now, there are many convenience methods to query for crystal structures, but we are going to use one of the most powerful method, which is what we call the query method, but now it has actually been changed into what is called a search method. So I'm going to change this example over here to be in line with what is in the notebook, okay? So let me go back to the notebook, and I'm going to show you how to use the materials project API, okay? So one of the things about Pymatgen and the materials project API is that these packages are not by default installed in Google Colab, okay? So Google Colab already has all the other data science and scientific Python packages pre-installed, so you do not need to do anything. But for Google Colab, you actually do need to install Pymatgen and the materials project API client separately. Okay, so what you will do is that you will call !pip install Pymatgen, and the API, because Google Colab runs on Python 3.7, we need a special version of it, which is given by this link over here. So all these are inside the GitHub repo. And what this will do is that it essentially downloads Pymatgen and the Materials Project API package, and it will start installing them. Okay, so you will need to give it a while. It doesn't take too long, maybe less than a minute. So you just need to wait for it. Okay, it seems that the install is done. So what you will see is that it actually warns you of something, which says that there were certain packages that were previously imported in this runtime. If you want to use the newly installed version, you need to restart the runtime. So I'll do that. Okay. And you don't actually have to run it again. Okay. Now, to use the Materials Project API, you need to import np raster. So this is actually the line that you need to import. Now, if you are using it in Google Colab, the way that you import it is using the np API package. Okay. Now, in order for you to use the Materials Project API, what you need is something called the Materials Project API key. Okay. Now, each of you will need to get that API key for yourself, right? And the way that you do this is that you go to materialsproject.org. Okay. Now, so this is the Materials Project. So it is, and if you do not have an account, you just click on this. You then register for an account. You can, of course, do it with your Google account if you wish. If not, you can do it via an email. I will use my Google account, which I've been using for quite some time. And I am now into the Materials Project. Okay. Now, to get your API key, what you need to do is that you go to the dashboard, and you will see the API key right here, right? Okay. So this is my API key. You will have your API key that you will use, and please do not distribute the API keys. All these are supposed to be secrets. Okay. Now, what you would then do is that you go back to this code. When you call np raster, you actually need to give it the API key, right? So the reason why I do not put it as part of the notebook in the GitHub repo is because, like I said, you are not supposed to be distributing your API keys. Okay. Now, once you give it that code, what you can do is that you can call this, and this basically says, I'm going to use the Materials Project np raster to do a search on the summary, and I want all documents belonging to some oxide system, right? So star means a wildcard, right? So it means one element plus oxygen. So, and the fields that I want are things like the materials ID, the formula, the formation energy per atom, and the band gap, right? Now, if I print out what the first item in the document is, you will see that it basically shows you, well, the first item in the document is this indium oxide, In2O3. It has the materials ID MP-1245202. It has a formation energy of 1.5458 something, and it has a band gap of 0.692, and so on and so forth. Okay, so so this essentially gives you a very quick way of grabbing lots and lots of data from the Materials Project. Okay, now maybe you want to know really how much data did I get, and you can see that I actually, in that one call, I have gotten information on 2,488 materials. Okay, so that is a lot of data, right? Now, maybe you want to know what exactly this indium oxide is. You can go back to the Materials Project website. Okay, let's go here. Start exploring materials. I can type in my Materials Project ID, and you'll see that they found this structure. This is basically the data on the materials project that I have just obtained via the materials project API key. Okay? And you essentially can see that you have all the different types of data that are available here. And things like what are the lattice constants and the structure of the crystal structure of indium oxide. And you can obviously visualize it. And if you want, you can download a zip file that you can actually view in something like Vesta. Okay? This actually gives you the documentation of the materials project API. It basically gives you information of what sort of things you can actually get from the materials project API. The one that we just used was basically what is called a summary. A summary is essentially just a very brief summary of the computed data for a material, okay, that is in the materials project. So you can see this is they actually have a complete list of fields that you can actually ask for. So, and this is going to be something that you are going to use very frequently, okay? You need to be aware that, well, I actually can also get things like the reaction energy per atom. I can get things like the band structure or the DOS from the materials project API using the summary method, okay? Let me go back here. Now, now that we have gotten the data, the actual list itself is not a particularly friendly format for us to do data science with. So for data science purposes, all of us pretty much prefer to work with Pandas data frames. So what you can do is that you can convert all that data into the Pandas data frame using by converting all the individual documents to dictionaries and giving it as a list to the data frame constructor. And you can see, and what you get is basically this nice little data frame with all the data in a tabular format that you can now work with, okay? And this is what you will actually be using for your machine learning models, okay? You can also do things like, well, if I only want the data with valid data, I can drop those with NA values, which is not applicable values. Here we don't actually have any non-valid data, so nothing is dropped. And yeah, and you can plot things like, well, what's the band gap versus the formation energy for all my data? And this is the scatter plot of all the data points, okay?